Hello everyone, my name is Qingyu from Stanford University. Today I want to talk about this question. For hydrogen and carbon dioxide underground storage, do they share the same modeling challenges? It is well known that human beings are faced with remarkable climate change because of greenhouse effect. Actually, not only human beings, polar bears also suffer from that. And among the overall greenhouse effect, nearly 80% is contributed by CO2 emission. Furthermore, most CO2 emission is from the combustion of fossil fuels. To address this, there are mainly two strategies to cut down the CO2 emission. The first is carbon capture and sequestration, which is known as CCS. It has been put into practice since the beginning of this century. The second is to reduce further CO2 emission. Since most of the CO2 emission is from the combustion of fossil fuels, the most important way here is to adjust the energy structure, which means we want to replace current fossil fuel with some clean energy sources, including solar, tide, wind, and so on. But one issue of renewable energy source is that it has fluctuation over a year. As shown here, there's a valley in the winter and there's a peak in the summer. So we need to figure out a way to store energy to compensate the shortage in winter. Given that we want storage to be emission-free, we choose hydrogen since it is the only emission-free for the reason that we want a midterm and long-term storage for multiple terawatt-hour, we choose underground. Overall, that's the reason we want to do underground hydrogen storage. So far, subsurface hydrogen storage has been successfully implemented in salt cavern and salt dome for the several decades. Here are some successful projects, but the issue of this is that the storage capacity of each cavern is really limited, and the salt cavern number is limited. Not every well has such cavern. That's why we want to do hydrogen storage in depleted reservoirs and saline aquifers. There is actually really little knowledge about underground hydrogen storage in depleted oil reservoirs and saline aquifers. The knowledge gap here is now filled with such a hypothesis that there is no technical limitation for hydrogen storage in depleted reservoir and saline aquifer. We can transfer the exactly same techniques we learned from CCS to hydrogen storage. But it is true, can hydrogen really be modeled exactly the same as carbon dioxide? So in this work, we want to start from the current knowledge we have already learned about hydrogen, which are physical and chemical properties of hydrogen, and then we want to explore if there are any extra challenges for hydrogen at the Darcy scale and at the Pore scale. So for physical properties, we can see that compared with carbon dioxide, hydrogen has less density, which implies greater buoyancy effect. Hydrogen has less dynamic viscosity, but higher kinetic viscosity, which means there will be less nonlinear initial phenomena. Hydrogen also has a smaller molecular size, which indicates it will have a greater Klinkenberg effect. For chemical properties, hydrogen will react more actively with other gas species mediated by bacteria. As a result, these chemical reactions will pollute hydrogen stored underground. Some of the products like H2S are poisonous and really easy to cause explosion. These chemical properties also make hydrogen really unique in the sense that the whole process would be a complex system coupling flow, mass transport, and microbial population dynamics. With the above properties, we can now look at if there is any difference at Darcy scale. In porous media, we know that once the scale reaches reference element volume, which is ReV, it is at the Darcy scale or continuum scale. And we have two-phase Darcy's law at the Gaussian equations at Darcy scale. If we assume all of these Gaussian equations work, what will be the difference of dynamic behavior given different properties? So we know for gas flow in porous media, there will be slippery near the solid boundary, which is named as Klinkenberg effect. This will increase the permeability of gas in the porous media. That increase could be approximated by 4 times of Nussen number. Nussen number is a dimensionless number to describe the ratio between mean free path and pore size. This means that it is associated with local pressure and local pore size. Here we discuss 3 typical geologic formations here, which have following mean pore size. For coarse sandstone, we assume it is 50 microns. For tight sandstone, we have 8 microns. For shale, the mean pore size is 50 nanometers. So from the plot, we can see that for low permeability rock like shale, hydrogen will have a more significant Klinkenberg effect. The apparent permeability could be 5 times greater than the intrinsic permeability for shale. This will largely influence the seal capacity of the cap rock. Since the permeability is also a function of some local properties like local pressure and local pore size, the heterogeneity of the system would be amplified because of this. Moreover, if two-phase Darcy's law hold here, displacement in the porous media may not be that stable. There will be some fingering effects like viscous fingering or capillary fingering, which is controlled by dimensionless parameters. Here is the famous instability diagram neglecting gravity. There will be some fundamental difference if 2 points lie in different instability region. So if we also include gravity into the phase diagram, then it will be a 3-dimensionless number controlled phase diagram. And then we plot the dimensionless parameter space for hydrogen and carbon dioxide in the same phase diagram. We find that hydrogen and carbon dioxide do not live in the same parameter space. The dynamic behavior of hydrogen lives either at the edge of the gravity viscous unstable region or in an area that has not been fully physically characterized yet. This clearly shows that there will be extra challenges for modeling hydrogen. So far, we always assume that two-phase Darcy's law is correct. However, whether the two-phase Darcy's law is correct is actually debatable. To study this, we need to start all the way from the down bottom of the problem, which is the governing equations in the Pore scale, Navier-Stokes equations. Here are the two-phase Navier-Stokes equations and boundary conditions in such a domain as shown in the figure. Then we non-dimensionalize the equation, but notice here there are 2 different length scales here, co-sample length scale uppercase L and pore size lowercase l. We non-dimensionalize the equation like this to make sure the energy introduced at the co-scale is dissipated at the pore scale. Then we got these following dimensionless governing equations. We can see that they are only controlled by these 6 dimensionless numbers. Of course, we can do the same thing for the boundary conditions, so we can obtain the dimensionless boundary conditions. So here we came up with such a question that when can these equations be reduced to two-phase Darcy's law with gravity, like these 2 equations? So it actually depends on the relationship between different force terms in the Navier-Stokes equations. We need the following 5 constraints to be satisfied, then the two-phase Navier-Stokes equations can be reduced to Darcy's law. The first constraint here is about the ratio between Pore scale and Darcy scale, which always holds true here because our co-sample is much larger than the pore size. The second constraint makes sure that there is no initial effects. The constraint 3, 4, and 5 ensure that the pore scale boundary condition could be reduced to this ideal Laplace law. But for our hydrogen, do these 5 constraints always hold true? Since we have got all of those dimensionless parameter space, we can check it by looking at these dimensionless number. So the result actually varies from different geological formations. Again, we choose these 3 typical rock types as the different mean pore sizes. So the different mean pore sizes decide what the length ratio here is. So again, we can see that for any of these three geological formations, constraint 3 is not satisfied because the mobility ratio is always much smaller than the order of magnitude of 1. And constraint 4 it is very interesting that for constraint 4, it differs from different geological formations. For shale, constraint 4 is true, but for coarse sandstone and tight sandstone, it is not true. This means that the reduction to Darcy's law actually depends on different length scales here. So in short, the dynamics of the hydrogen will not behave as two-phase immiscible displacement since some of the constraints are violated based on the dimensionless parameters we have already got for hydrogen. There could be some complex dynamics behavior at pore scale. So we so far have already stated the difference theoretically with the equations. So to further state this fundamental difference between hydrogen and carbon dioxide, we simulate a classical Taylor problem. So we inject water and gas from two inlets, and then we observe the flow at the horizontal part. We use volume fluid method to solve this two-phase flow problem. Volume fluid method is just another form of Navier-Stokes equation, and the boundary conditions are as this table shows. All the simulation cases are set up in open form, which is an open source PDE solver. Here are some results. We try different velocity pairs. The blue phase here is the gas and the red phase is water. So under this injection rate, we can observe that for carbon dioxide, it is stratified flow, like a fractional flow. But for hydrogen, it turns out to be a bubbly flow. We can see a lot of bubbles generated in the middle of the channel, and it separates the red phase. Of course, we tried some other velocity pair like this. So for this velocity pair, CO2 is still stratified flow, just a fraction of two different fluids become different. And interestingly, now the hydrogen turns out to be a slug flow. It is very different from the bubbly flow. You can see the blue phase separate the red phase into some discontinuous part, and there's some slugs here in the horizontal channel. We also tried this velocity pair. Again, for carbon dioxide, it's still a fractional flow, still a stratified flow, which has a different fraction of two different fluids compared to the previous two velocity pairs. But for hydrogen here, it goes to be a stratified flow just the same as carbon dioxide. So the results are summarized in this table. So from the visualization of simulation results, we observe bubbly flow, slug flow, and stratified flow, and they may vary from different velocity pairs. For complex flow patterns like bubbly flow and slug flow, Darcy's law fail here since there's discontinuity at pore scale, so that the key assumption of Darcy's law that a percolation-like displacement pattern is clearly violated here. This also makes difference between these flow patterns not trivial at all. That's why we believe that different properties would lead to fundamental difference between hydrogen and carbon dioxide. Extra modeling work would be required to fill the gap from equations at Pore scale to equations at Darcy scale. With this, we draw a conclusion here. Compared with carbon dioxide, hydrogen has a stronger Klinkenberg effect, which leads to more heterogeneity and higher permeability. More microbiome-mediated reactions are expected, for which the system becomes much more complex. At Darcy scale, we clearly see that hydrogen lies in a different dimensionless parameter space and different instability region, based on assumption that Darcy's law is true. At the Pore scale, we discussed whether two-phase Darcy's law holds true from the perspective of theory and simulation. We find that there are dramatic differences in the type of flow regimes, which lead to knowledge gap from Pore scale to Darcy scale. To summarize, we think that further research is needed to develop, test, and validate new models against experiments at different scales. Thank you all for listening to my presentation, and I'm willing to take any questions you have. Thank you.